Welcome to course 36, or course 2, lesson 36. In this lesson, we're going to deal with ratios and sample space. We're going to write a ratio in 4 different ways, all of which are equivalent. We're going to name the 3 numbers involved in a ratio. We're going to identify the sample space of an event, and we're going to learn different methods for determining a sample space. So let's get started. Our vocabulary. Let's start first of all with fundamental counting principle. What this says is this: if there are m ways for A to occur and n ways for B to occur, then there are m times n ways for A and B to occur. So what we do here is, for example, if A was a cube, and we know that a cube has 6 numbers on it, and we're going to roll a cube, plus we're going to spin a spinner that spinner has 4 numbers on it. If we do both of those things, if we roll the cube and we spin the spinner, how many total combinations do we have that could be made with the cube and the spinner would equal 24. That's what the fundamental counting principle is. Rather than you having to go, okay, 1 and 1, 1 and 2, 1 and 3, 1 and 4. There's 4, and then we got 2 and 1, 2 and 2, 2 and 3, 2 and 4. There's another 4. And then just keep counting them up. Eventually you get to 24. Well, the fundamental counting principle makes it so that we know that there's 24 right off the bat. Ratio is a relationship between 2 numbers, and sample space is just the list of the possible outcomes that we can get. So, a ratio is a way to describe a relationship between 2 numbers. For example, if there were 12 boys and 13 girls in a classroom, then the ratio of boys to girls would be 12 to 16. One way to write that is as a fraction, 12/16, which would then be reduced to 3/4, meaning that for every 4 girls, there's 3 boys. So the ratio is 3 to 4. So that could be, because we reduced the 12/16 down to 3/4. So that can be written as 3 to 4, 3 over 4, 0.75, or 3 to 4 when we're talking about boys to girls. If we were talking about girls to boys, we'd have to flip everything back where it'd be 4 to 3, 4 over 3, 4 to 3. Everything would change. 1 to 0.75. So most ratios involve 3 numbers. Even though only 2 numbers may be stated, there's an unstated number. For example, in our ratio of boys to girls, we knew that for every 3 boys, there's 4 girls. So if that were the total in the classroom, then that would mean that there would be 7 students totally in the classroom. Or if our ratio was 6 to 8, then we'd know that we had 14 students. Or if we had a ratio of 5 boys to 8 girls, then we know that we'd have 13 students. So we can figure the unknown. So in a class of 28 students, if there's 12 boys, and it's a class of 28 students, how many girls are there? So what's the boy to girl ratio? Well, we can find this missing simply by doing mathematics, subtraction 28 minus 12, and know that this is 16. So our boys to girls, and this is total, so we got 12 boys to every 16 girls with a total of 28 as total students. So what is the boy to girl ratio? The boy to girl ratio is 12 to 16. What is the girl to boy ratio? 16 to 12. We just take the girl first. And then we reduce it down to 3/4 and to 4 to 3. Got to remember to reduce that down. We do not change the ratio to a mixed number. We leave it as 4 over 3 and 3 over 4. Okay, so if a team won 4/7 of its games and lost the rest, what was the win-loss ratio? Meaning for every game they won, how many did they lose? The way we calculate this type of problem is that the team won 4/7 7ths of its games. So they won 4 out of every 7 games. So that means that they lost how many games? That's right, they lost 3. Because for every 4 games they won, they lost 3. So they won 4 out of every 7 games, and they lost 3 out of every 7 games. So their win-loss ratio is 4-3, or 4-3, or 4-3. Okay, if there are red marbles and green marbles in a bag, let's go ahead and do that. We've got red and we've got green, and this is our total marbles. If the ratio of red marbles to green marbles is 4-5, so red marbles to green marbles, so red comes first, green comes second, so red marbles to green marbles is 4-5. What fraction of the total numbers of marbles are red? Well, in order to get that fraction, we have to know how many our total marbles are. Well, if it's 4-5, what do we get? What's our total? What's this down here? Well, we just add those two together. It's 9. So if we're pulling out, if we have a bag that has 4 red marbles in it and 5 green marbles, there'd be 9 marbles total. Wouldn't our ratio be 4-5 of red to green? It would. So the fraction of red marbles is 4/9, or 4-9. Does the bag have to equal 9? Does it have to have exactly 9 marbles? No, it doesn't, because the ratio is 4-5. We could double all of these, right? Times it, do 2/2 and have it 8-10, and have there be 18 marbles. That would still reduce down to 4/5. But our answer is 4/9. And our answer down here, in regards to do the numbers have to equal 9, is no, it doesn't. We could have, like I said, 8 and 10 and have 18 marbles instead of just 9. But it's important that you set it up correctly. Now let's talk a little bit about probabilities. The probability is the event that's going to occur. We're going to talk about our favorable outcomes. That means what are we looking for versus how many could possibly come out. So, and we've learned that before. What we need now we're going to talk about is listing the outcomes, what the possible outcomes are, which they call sample space. So we're going to do 3 examples here. First one is flipping a coin. Well, if you flip a coin, what can you get? What can possibly happen? Well, the only thing that could possibly happen if you flip a coin is that you get heads or you get tails. Those are the only 2 outcomes that you could have. So your sample space for A would be heads and tails. That's your only choice, is a heads and tails. That's the only thing that could possibly come up. For B, your possible outcomes on a cube, meaning a dice, a number dice, how many numbers are on it? There are 6. So your sample space there would be 1, 2, 3, 4, 5, and 6. That would be your sample space for a cube. And for the alphabet, your sample space, of course, is going to be much larger because there's 26 letters in the alphabet. So you're going to have A, B, C, ellipse, ... X, Y, Z. Right? That would be your sample space for one letter from the alphabet, would be listing all 26 of the letters. That's sample space. That's what they call sample space. So when you're asked to list sample space, you're listing all of the favorable outcomes that could occur. So let's look at this. A coin is flipped. Okay, let's just start right there. It can come up heads or tails. That's our sample space for our coin. Right there, we've already listed it. And a spinner is spun. Well, here's our spinner, and our spinner has 4 possible outcomes. So each time we spin it, we could get 4 outcomes. So we flip a coin, we spin it. We flip a coin, we spin it. All right, so we have one coin that we toss the coin and we spin one time. What's the probability of the heads and a number greater than 2? So every time we flip it in heads, we get heads and a 1, a heads and a 2, a heads and a 3, a heads and a 4, or we get a tails and a 1, a tails and a 2, a tails and a 3, and a tails and a 4. So this is our sample space. That's our entire sample space of outcomes. Now we got to find out how many times, what's the probability of heads and a number greater than 2. Do we need to even worry about the tails? We don't. So we come down here to heads, and we got heads and a number greater than 2. It's right there. It could be heads 3 and heads 4. So we have 2 favorable outcomes. 2 things that would fit this category up here. 2. And how many are our total choices, our total possibilities? Are 1, 2, 3, 4, 5, 6, 7, 8 over 8. So here's our heads and numbers greater than 2. We have 2 of our 8. So our probability is 2 eighths, which then reduces down to 1/4. So our probability of getting a heads and a number greater than 2 is 1/4. These will take some practice. These can be confusing at times. It's really simple, but until you get it, wrap your mind around it, they can be a little bit tough. Okay, so in this example, this one is quite detailed, so I'm not going to have you do it. I'll just kind of walk you through it. We're going to use the fundamental counting principle down here. Remember what that was? So that you can do. So for spinner A, we know that there's 5 here. And for spinner B, we know that there's 6. So what are our total possible outcomes? If we use the fundamental counting principle, we're going to times those. So our total is going to be 30. We know that. So let's go to our question. It says, find all possible outcomes when the 2 spinners are spun at the same time. Well, that's going to be 30, but that's not listing them. So we're going to have our possible outcomes would be J1, J2, J3, J4, J5, J6. K1, K2, K3, K4, K5, K6. L1, L2, L3, L4, L5, L6. M1, M2, and we're going to list all of those. And it's going to look like that. That's what it would look like. And as you can see here, you've got 1, 2, 3, 4, 5, 6 by 1, 2, 3, 4, 5, 6 by 5. You count all those up, you're going to end up with 30 outcomes. So it says, what's the chance of us getting M and the number 3? Well, it's right there. There's only one M3 on that entire chart. So what's our answer going to be? It's going to be 1/30. Or 1 in 30. I know that's a lot to take in. We'll do this many times. You'll get it down. Believe me, you'll understand it. All right, here are your numbers. Your tickets in the door are 10 AB, 12, and 27. Thanks for watching. Bring your questions to class. We'll go over them together. Appreciate you. Keep up the hard work.